Good morning, everybody, and welcome to this latest UKDEA webinar, latest in a series we've been running throughout 2021. This morning's event is about the practical application of heat pumps. We've been literally taken by storm by the number of people who wanted to attend. We've got over 230 registrations, so there's still lots of people coming into the room as we speak. So I'll kick off, and while we're doing that, I'm sure a lot more people will join. But we've already got hundreds in at the moment, which is really good. So moving onwards. So just by introduction, my name's Simon Woodward. I am the chairman of the UK District Energy Association. We're hosting this event today. Just a little bit about ourselves. So we're a non-trade, non-for-profit association. We're a bit unusual. We were started by a group of local authorities over 10 years ago, so 11 years, 2021. We were started in 2010 with 6 founder members by the main local authority-led schemes at that time. Back in 2010, district heating, district energy wasn't really commonplace. It wasn't really talked about. There wasn't really a sector. Each scheme was individually trying to do its own thing, whether it was in Sheffield or Southampton or Woking. And we collectively got together and we formed the UKDEA. At the heart of the UKDEA are the scheme developers, owners and partners. So as we say, the ones who face the financial pain each day of growing and developing district energy schemes. So there's about 20 full members in the centre. And around the outside, we've got well over 100 associate members, the really important people who make up the bulk of the sector in terms of numbers. So whether that's equipment suppliers, consultants, advisors, interested local authorities, service providers, etc. We've got over 130 members. We've grown a lot in the last year. 27 new members in the last year, which is excellent, and all major district energy schemes in the UK are represented by the UKDEA. So moving on, what do we offer? Why do people want to join the UKDEA? Why do you want to get involved? So we provide the tools and support that members need to build, grow their schemes and develop their business. So people join for many and varied different reasons. So we're an expected voice for raising concerns to the government. That was the primary reason we were created all the 11 years ago, was to act as a voice for the sector. So that underpins everything that we do. We have a 50-page monthly journal that we circulate to all members. So that's a brilliant place to be a shop window for what you're doing, talk about things that you're doing, press releases, news stories, case studies, find out about what's happening in the sector, what the government are doing, etc., etc. We have an annual conference at AGM, but on top of that, we have regular information and networking events, such as the one today. So we've been running a series of very, very successful webinars throughout 2021 to showcase your expertise as members, your products, your services, and you'll be hearing from a number of those members today. We've got a feature-packed website and an information library, which is literally just going live. So that's absolutely packed with district energy documents. So that's a member-only benefit. And we've also got things like promotion of the DE sector through events such as Future Build 2022. So those of you who've been around for a few years may remember EcoBuild. Well, EcoBuild has morphed into Future Build, the big low carbon, low energy exhibition at the Excel Exhibition Centre that will be taking place in March 2022. And we've got back together with Future Build, and there will be a district energy pavilion at Future Build 2022. We also have a training register with a very large number of courses offered by members. So if you want to join and you've got a course you're offering, we can put that in the training register, and help, advice and support. Most importantly, a network of 130 members working together to assist each other and as a voice for the sector. And I think what really pleases me, nothing more, is when I see members collaborating, working together, talking to each other to develop the sector and to build their businesses. So why heat pumps? You hear a lot about heat pumps. They never seem to stop hearing about heat pumps in the news. Well, we had a waste heat event earlier this year to look at the scope for utilising waste heat in district energy networks, and that clearly identified the significant role for heat pumps. But they're still an emerging technology. They're not widely understood. I mean, it's unlike gas-fired CHP, and gas-fired CHP was obviously the technology that many of us were using to power heat networks for the last 20 years. So if you go back over 25 years ago to the late 1980s, early 1990s, I think, in my view, heat pumps are where we were with gas-fired CHP at that time, not widely rolled out, not widely understood, lots of bad installations happening, people very nervous about this new technology. So what we're trying to do in the UKDEA is to run a series of events to help the sector understand heat pumps and how they can be successfully incorporate into heat networks. So today specifically, we've got 5 really good focus presentations on specific aspects, ranging from Lyall from SSC about air recirculation, Ken from Solid Energy, who'll be talking about network temperatures and COPs, Pablo doing an interesting presentation about ammonia risk assessment, so something that people can commonly think about when using ammonia heat pumps. And we've got Matthew King from Hilson Moran about the practicalities of incorporating heat pumps into heat networks in place of gas-fired CHP solutions. And then finally, we've got David Birks, who'll be doing an interesting presentation on using open borehole solutions with water source heat pumps. So some real good practical presentations about heat pumps and how they can be used in district heating networks. So just a couple of final slides for myself before I hand over to the first presenter. So future events. So for all delegates, anybody on the call today, we're actually in the process of finalising our next webinar. Our next webinar is about system optimization. That's a very big topic, system optimization, ranging from pumping to controls to temperatures to design to etc. etc. You name it. It's a very wide, broad church. So if you want to find out how to optimize your district heating system, whether it's under development or an existing one, then this is for you. Please look out for further details. And if you're a UKDEA member, you are very welcome to get involved and to speak at that event. So finally, before I bid farewell, and I'll say hello periodically when I'm introducing the various speakers, if you want to discuss joining the UKDEA and our growing voice, please do drop me a line, give me a ring at the number above, and be really pleased to speak to you. So if I can welcome the first speaker to the stage, please. So this is Lyall. Lyall Archer is from SSC, and Lyall will be talking about the impacts of air recirculation on air source heat pump performance, and I will leave him to carry on talking about that. So Lyall, if you're okay to join the stage, please.
Hi there, can you hear me?
Yeah, I can hear you fine, Lyall. Your camera's off. Oh, it's brilliant.
There we go.
On now.
Here we go.
Thanks, Lyall.
Perfect.
I'll leave you to it. Thanks very much.
Now.
Yeah.
Great stuff. Yeah, first of all, thanks for having me on, and thanks everyone for joining. Fantastic turnout, so really appreciate that. I'm Lyall Archer. I'm a process engineer within SSC Energy Solutions Distributed Energy Group. And I primarily support on the decarbonisation of our existing portfolio of heat networks and the design of our new ones. I'm here today to talk about what I think, and I hope everyone will agree by the time I finish speaking today, is a really interesting and worthwhile piece of work that we've done. And that has hopefully shed some much needed light on a risk to the technical viability of DH scale air source heat pumps that we've investigated. We'll also look at this in the context of an actual application or a real case study to one of our operational heat networks. And that issue that we're going to discuss is the potential for performance degradation and cold nuisance as a result of air recirculation through these large DH scale air source heat pumps. So if we can just jump in the first slide. That's can we see that? Perfect. So just to kind of set the scene and give a bit of a context to the issue that we're facing. The challenge that we've got is the majority of our heat networks in the UK are in urban environments, and obviously the government have advocated air source heat pumps as a key enabler for decarbonisation of these networks. The benefits of the air source heat pumps, as I'm sure we all well know by now, they're highly versatile. We can place them just about anywhere. Air is an inexhaustible source of heat, so no issues with running out of a source of or a supply of heat there. They're also cost effective, so the capex for interface with ground or water source for water source heat pumps is can be quite extensive. Typically, some of the large groundworks or capex elements that you would otherwise need for those systems aren't required for air source heat pumps. So that's a huge benefit. There are some risks though, as we well know. The efficiency in the COP has to be as high as possible as a result of the high electricity tariffs or electricity costs versus gas costs, and that means that obviously the efficiency of our heat sources or our heat supply needs to be as high as possible to ensure the economic viability. and particularly the issues that we're investigating today, which obviously relate to the efficiency, but are more centred around this air chilling and cold nuisance issue. So essentially, to describe the problem, whenever we remove air in large quantities on a localised scale, or remove heat from the air, sorry, on that localised scale, this can cause a quite substantial reduction in ambient air temperatures. And the net effect of that is that we get, or we can see, cold nuisance temperatures. So essentially, you're just cooling the local air around if there's residents or pedestrians in the nearby area. And then there's also the potential for visible cold plume formation as well. Under certain ambient air conditions and environmental conditions, you can essentially produce plumes of smoke. And we've kind of shown a snippet from the CFD model, which I'll go into a bit more detail on the right there in yellow, shows a cold plume extending from the V banks of a air source heat pump array. And yeah, the other issue that we've got with this cold or this air chilling is that when the heat pumps will cool the air and then recirculate the air as they draw in to feed the next round of heating, you can get this recirculation effect where the cold outlet is just fed to the inlet, and it continues and continues. And what then happens is that you get a accumulating snowball effect on that local area, local air temperature, as the heat pumps continually cool. And the kind of negative effect that we're seeing with this is that this will detrimentally affect the COP, because your inlet air temperature will keep reducing and reducing. So not only will that affect obviously your economic viability, but it can also affect the heat pumps from operating. They will reach eventually a minimum inlet temperature or condensation temperature where the heat pumps will start to derate if the air temperature gets too low. So that's an issue that we've obviously got to investigate and see if we can solve it. So just to give an overview of the case study that we're investigating here. This is one of, let's just move to the next slide, sorry. There we go, sorry. So this is one of our largest heat networks in central London. It serves over 2,000 residential units, and it's got an annual heating demand of over 10 gigawatt hours. This network's fueled exclusively by natural gas, as we see with a lot of the existing networks that we've got. There are plans to expand this to over 5,000 customers in the next 10 years. And as part of that, for planning permission for the new phases to be obtained, they must comply with Part L of the new building regulations, which essentially means they've got stringent SAP factors. And in other words, they can't be served purely by natural gas. So the solution that we've developed, and this is again something that we'll be seeing a lot of in the coming years, will be removing a CHP engine and replacing it with 3 megawatts of air source heat pumps, and they'll give over 70% of annual heat demand contribution at full build out, with the remaining 30% to be fueled by top up gas boilers. So new connections to this network will comply with Part L in this case, and we've been looking to develop this air source heat pump solution to a kind of pre-detailed REBA 3 design stage. There's a couple of site-specific challenges that we've seen here. So there's limited potential for water source heat pumps. So the client, and again, this is something we're seeing more and more often, is that the client will actually specify that they want air source heat pumps as the solution. And with that, we had a limited availability of rooftop space to site the air-cooled heat exchangers. So there was nowhere on a basically high level that we could site them, which is an issue that I'll drill into a wee bit more. But we were given a plot of ground at ground level, which we've been told that was where we had to site the heat pumps and the heat exchanger. So we've had to deal with that, which is a bit of an issue. And obviously it's a very built up area that we're dealing with. There's some residents very nearby. There's one domestic property basically right beside the plot of land that we've got there, so that those air chilling and cold nuisance and visible plume issues were obviously going to be pertinent in that scenario. And yeah, the things that we have to consider there is obviously the visual and the acoustic impact and the comfort to these residents. So as we've said, we wanted to go and investigate that, and that's exactly what we've done. So we've commissioned a CFD study, or modelling study, with one of our partners, Joel Gustafsson Consulting. And the objectives of this were obviously to quantify the performance degradation due to air recirculation for that particular installation, and determine the likelihood of cold plume formation. And then what we wanted to get out of this was essentially to propose mitigative design measures so that we can ensure that these issues don't manifest when we actually install the system. So the building massing in the surrounding area was built into this sim scale CFD model to replicate the kind of relative impacts of the geometry and massing of the buildings in the area with respect to kind of breaking wind or windbreaks, sorry, and the kind of flow characteristics of the air through that area. The environmental conditions that were modelled were based on UK conditions that were more prevalent UK conditions that were most likely to produce visible cold plumes. This is well, our partner could explain this in a lot more detail, but it's due to the kind of relative humidity and temperature conditions where cold plumes are likely to form. And this is typically around about 1 to 2% of the year on an annualized basis, but it is a significant likelihood, or is a significant enough likelihood that we would need to investigate it and model on this worst case scenario. And what we essentially did was tested a typical heat pump and cooler arrays without any preventative measures, so a kind of base case just to see what the effect of it was. And once we did the initial modelling, the effect of it was this quite scary picture, which we see in this slide. So lots of pictures here, so I'll kind of take time going through these, but we based the initial modelling on V-bank and flatbed coolers, different orientations of plant. Obviously, we did the base case or sought that the base case would mitigate visual impact and equipment footprint. So what became very apparent very quickly is that the negative effects of the air recirculation that we discussed in this kind of base case were very severe. We had cold plumes, 7 degrees below ambient, extending kind of far out in the road. You can see that the first picture with the kind of orange splodge is a cold plume across a kind of 50-meter area, and you can see it actually touching that residence building right beside the installation. The surrounding area would be significantly colder than ambient. It was an average of 12 degrees all year round because these heat pumps are operating on a continuous 24/7 basis to provide the base heat load for the scheme. The net effects of that operating continuously had a 12-degree reduction in ambient temperature, which is obviously less than desirable. Maybe nice on a summer's day, but certainly in winter that would be less than comfortable. The worst impact that we saw was the heat pump COP. So it was drastically diminished, so much so that, as we had alluded to earlier, that the heat pumps actually turned off due to the minimum air inlet temperature being reached, or we simulated that the heat pumps would turn off. So the net result is that this solution wasn't technically viable in any way. So we went back to the drawing board because the issues, or the magnitude of these issues, were so severe. Back to the drawing board and came up with some design alterations that to do with essentially the selection of the coolers, the orientation of the plant, a couple of other things, such as increasing the number of the heat exchangers, so reducing their temperature delta from 6 to 3 degrees. So instead of the heat pump reducing the air temperature by 6 degrees, or the air cool exchanger, sorry, it reduces it by 3 degrees, so that the net kind of cooling of the air on an individual basis was reduced. We also increased the mounting height of the heat exchangers, and this is something that's really important. The higher up that the heat exchangers can be, obviously the freer the air is to move through and take away that cooling there. So once we implemented these changes, we went and remodeled it and got some much nicer results. We did a number of simulations, and there was a fairly substantial amount of computational horsepower needed and time to do this. But as we said, the results were significantly improved, so much so that we got a workable solution, something that would be technically viable. You can see on the right there the 7 degrees below ambient, which is your visible cold plume risk condition, is just that tiny wee bit of green extended from the air coolers there. So basically, we've mitigated that issue. It's not going to be a concern. The air recirculation on a macro level was reduced to almost zero, so we were seeing a minimal adverse impact to the heat pump COP. As we said, the risk of cold plume formation was mitigated. The reduction in the local cooling effect was mitigated as well. And we're seeing at the worst case, a 3 degree, maybe 2-3 degree reduction. You can see that in that temperature plot in the bottom right there. And basically, your ambient air temperature is the red, and then you're seeing very local to the heat pumps, kind of half degree gradients in the temperature reduction around there. So nothing that would cause significant concern or impact to the residents in the nearby area. So once we've actually verified these results through continuous or further iterations of the model, the constraints that were imposed by the new plant design were incorporated into that REPA 3 structural design. And that involved, the urban design, architectural, the acoustic design, obviously to mitigate the impact of the residents, making sure that the solution would work. The structural integrity of the new energy centre, the maintainability of the access, and then all of the safety considerations on top of that as well. So the fire strategy, the DESIR, and the ATEX rating. So all of these things were considered, and we've got to something we think is a workable and real solution. And because everyone loves that before, during, and after, we'll just give a view of this. This is the plot that we were given to work with. So you can see an area of kind of underutilised grass. The rest of this area that you can see around the perimeter of the wall is actually a lovely park. And this was a kind of piece of land that wasn't particularly well utilised. And so we've hoped to regenerate that into something that is a lot more visually appealing. So here's our during picture. So this is when we've modelled the new energy centre with the heat pumps in a kind of semi-basement and the air-cooled heat exchanger sitting on top. There was then a kind of physical plenum which was placed between the inlet and the outlet of the heat exchangers to basically stop the air from recirculating, and that's one of the key things which I'll draw on in the conclusions. But yeah, we designed the kind of plant installation, and then to make it look nice and to make it visually appealing and to mitigate the acoustic impact, we got some architectures and urban designers involved to get us to something that we think would hopefully get through planning if we ever get to that stage, which I hope everyone agree it was certainly an improvement on the existing area, and given the potential visual impact of an energy centre sitting right beside a block of flats, a block of very nice looking flats, by the looks of things. We've looked to change this area into something that could be quite useful for local residents. So just to summarise with a couple of conclusions, and I won't read all these in depth. I'll just leave them up there for everyone to peruse at their own leisure. But the kind of key ones or key guidance for air source heat pump system design that we would propose, that we've, as a result of this or from the conclusions of this modelling, is that obviously the impact of these issues shouldn't be overlooked, and the consideration of the air recirculation should be integral to the outline design and any feasibility studies. And this is specifically with regards to location of the heat pumps and the air-cooled heat exchangers. So our kind of key conclusions would be: can space be made on a rooftop? Obviously, the higher up these are, the more, or the higher rate of airflow would go over the air-cooled heat exchangers and drag that cold air away. So can you put it on a rooftop? And if you can't, can you put it somewhere which isn't shielded by other buildings in the area? Because that has a quite drastic effect on the air recirculation. And if a location at height is used to site these air coolers, so if you are placing the evaporators on a rooftop, how closely can the heat pumps be located? And what we've seen as well is if you have a large separation distance between the heat pumps and the air coolers, it means, oh sorry, my phone's just dropped down there. It means that you have to sometimes introduce a brine loop, which can impact your COP. And then just on the next one, the result of the study and any recommendations from doing an airflow study should be incorporated into the pre-detailed design, and that should then influence the selection, the procurement of your air source heat pumps, as we're seeing with a number of our other schemes at the moment. And then just the key kind of design considerations: if you can't do a CFD study, or if you don't have time to investigate the issue, these are the kind of the rules of thumb. You should always put a physical barrier in between the intake and the outlet of the heat exchangers to stop that recirculation. You should always minimise your air cooler temperature delta, so basically putting in as many air coolers as you can, or as is technically feasible, with as low a temperature delta as possible, and reduce your fan speed increase your fan speed as much as possible to increase the ejection air velocity from the air-cooled heat exchangers. But then you've also got to consider the impacts that will have on the acoustic impact. So obviously the faster the fans, the lower the air recirculation issues could be, but then obviously the higher the noise levels are. And that's something we've seen without this project, is that we've had to balance acoustics, visual impact, and the air recirculation quite finely. That's me. Thanks for listening. And if anyone's got any questions, please feel free to put in the chat as the other presentations go on, and I can answer them. Otherwise, I can happy to stick around for the Q&A later and answer anything then.
Yeah, thanks very much indeed, Lyall. Really interesting presentation. Yeah, there's loads of questions in the question session, so lots of interest in your project, Lyall. If you can try and pause from answering those in the questions, but think about them, because then we can wait for the Q&A session at the end. That'd be really helpful. But if you can have a look at them in the meantime, some of them are quite testing, I should say, so they might need a bit of thought as to how you want to respond. But thanks very much indeed. Really interesting presentation, Lyall, and thanks very much. I'll ask you to leave the stage, please, and invite Ken to come on the stage. Ken Kneale from Solid Energy, who's making a presentation about operating temperatures on heat pumps and the importance of flow and return temperatures. So I can see you, Ken. So I'll step off the stage and leave you to it.
Thank you, Simon. Good morning to you all. Thank you, Lyall, for that excellent presentation on your project. Solid Energy make large heat pumps in Denmark, and very large heat pumps they are. They can be up to 5 and 10 megawatts. We use hydrocarbon as our refrigerant. Heat pumps are one of the main heat generators in the Danish district energy sector. They have many advantages. They can use carbon-free electricity, of course. They do not produce any emissions on site to pollute the air, but they do need to have some assistance to become more efficient and to produce more affordable heat for district heating consumers. Of course, there are many heat pump manufacturers. Other heat pumps are available. I'll be talking this morning about heat pumps in general, and nothing really is specific to Solid Energy. Certainly the principles apply to all heat pumps. I'll just bring the next slide up rather than go through that one. The Solid Energy heat pump selector that you see here has been designed to assist with large heat pump projects at an early feasibility stage. It can provide basic data on dimensions, electric power requirements, and a SCOP figure. SCOP, for everyone's information, is a seasonal average of efficiency. And it can give these SCOP figures for set parameters, and the impact of both groundwater temperatures and poor flow and return temperatures can be easily demonstrated. The heat pump selector has newer versions, but this older version, which I'm using today, and the new version, has been well received with many designers throughout the UK and Ireland. What I want to show today is the impact of high flow and return temperatures on the efficiency of heat pumps. This slide here, it shows that we have the red line is the heat output of the heat pump. The green line is the electrical input. The blue line, which falls as the temperature rises, is the heat demand from the system. And the blue line on the adjoining graph is the COP. So with the water temperature, the ground source water temperature from this example happens to be a mine shaft, it's 10 degrees C, with a flow of 85 and a return of 75, we end up with a COP of 2.3. That is obviously 1 kilowatt of electrical input in and 2.3 kilowatts of thermal energy out. Now, if we change the flow and return temperatures, we're beginning to see now the impact on the efficiency of the heat pump. So here we still have the water temperature at 10, that has remained constant. We have a lower flow at 70, a lower return at 60, but we now have a COP of 3. So we're beginning to head in the right direction with COPs, and that is only being affected by the flow and return temperatures of the system. All the other aspects of these heat pumps is consistent. There's nothing else that's changing. If we move on to the next slide, again, we've got everything the same. Here we've got lower operating temperatures, similar delta T. We're now up to 3.25. And to move further on, we've got a really good COP of 3.5. And this is because now we've got a flow of 70, a return of 40, a healthy delta T, and a really good COP number. This is possibly the ideal scenario, where we've got flow of 60, return of 40, and a COP of 3.75. Now, to summarize those, we've put together a very basic table which goes from 85, 75 right down to 60, 40, and we can see on the fuel savings that it's over 38% is possible. And that demonstrates that the cost of ensuring the right conditions that are met, the investment that's needed perhaps to reach these flow and return temperatures will be well rewarded over the lifetime of the project. Just to show the impact still of flow and return temperatures, on this slide we've increased the source water to 20 degrees C, and I think there's an overwhelming assumption that this will sort of dramatically increase the efficiency of the heat pump. Well, to be honest, it does increase the efficiency, but it only has marginal effect. The main influence on the efficiency is on the on the flow and return temperatures. This is another table showing the source water at 20 degrees C and the flow and return temperatures, and here we can increase it to potentially 42% better than our base numbers. And if we join them all together, combine the tables, we can see that 20 degree C water is slightly better than 10 degrees, but the operating temperatures are shown to be so much more influential on the COP numbers. I just wanted to show you another slide. This is where, to go back to Lyall's presentation, this is an air source heat pump, just as a comparison. Here, of course, we have to remember that our energy source is so much variable. The air temperature here we have on the scale of -10 to +18. For the COP varies hugely. The blue line going upwards indicates that. The kink in the middle, by the way, is the defrost cycle, which is required at temperatures just above freezing. When we take 5 degrees, for an example, out of the air, we can very easily freeze the equipment. So that kink is the energy that we have to use to defrost the equipment without having any impact on the output. By the way, we defrost the evaporators in sequence, but that has a negative effect on the COP, and it just is shown in a kink in the middle. So we've got a much more variable COP. This one happens to run from 2.2 to 3.2, totally dependent on air temperature. The reason, of course, that we used the ground source to indicate the importance of flow and return temperatures was very much to use the consistent temperatures that we get from water. This is an example of our calculator that we are using now. It's freely available if anybody wants to ask me for a copy. It's been specifically designed for the UK market. Unlike the UK, the heat pumps in Denmark are very much in rural environments. Even if they're providing district heating, the district energy centres are on the perimeter of towns and villages. Unlike the example we just saw before, the evaporators tend to be in the middle of a field where nobody's interested much in cold air dispersal or noise. So there's certain problems that have to be overcome to adapt the technology to the UK, and we believe that we've come up with many answers. Just to digress slightly, we've also got a thermal store calculator, which is useful, especially now when we need to potentially pick up cheap overnight electrical tariffs. Thermal storage is really essential for that, and also to reduce costs. We're now looking at thermal storage as part of demand side control, where the grid can instruct large heat pumps to come on and off, and we can add potentially 20% savings to the running costs of heat pumps if we bring in demand side control. So that's very much the end of my presentation, and I'll be available for questions later on.
Brilliant. Thanks very much, Ken. I thought that was a really interesting presentation. Particularly, I've not seen it done in that way before, about comparing the flow and return temperatures with the extraction temperature and the effect on COP. So I thought that was a really useful, simple way of doing it. So thanks, Ken. Thanks very much. Okay, there are a couple of questions in the chat for you, Ken. So if you can look out for those, that'd be really great. So if I could invite Pablo to come and join me on the stage, please. So Pablo is from Gexcon, and Pablo will be talking about ammonia risk assessment in relation to the application of heat pumps. So thanks very much, Pablo, and over to you.
Thank you, Simon. Thanks UKDEA for the invitation. So yes, as the title suggests, we're talking about how advanced consequence modeling can help in ammonia risk assessments. The study basically the studies that are going to show are based on 2 real case studies of work that have been conducted within our consulting department here in the UK. So before jumping into the presentation itself, I just wanted to give you a brief introduction of who we are. Gexcon UK is part of Gexcon International, a company with headquarters in Norway, which is a world-leading company in the field of safety and risk management and advanced consequence modeling. Besides offering a wide range of services to our clients in the safe and risk aspects, we do develop and or commercialize some of the most widely used and respected tools for conducting consequence modeling. It could be when we have a large suite of those tools, ranging from 2D simplistic up to 3D and more complex, which I'm going to talk briefly in my presentation. So jumping now into the interesting stuff as well, and giving a bit of introduction and background of what we are going to talk today. We know that all refrigeration systems do require risk assessment, and ammonia systems are no exception. So appropriate type of assessments may include the zero assessment, which stands for the dangerous substance and explosive atmosphere regulations. Process hazards analysis types, as could be like HAZOPs, SILS and LOPAs, which would more typically include and review operational faults, process controls and causes and effects, and so on. But the thing is that, of course, knowing that heat pumps use toxic anode flammable working fluids, it is very important to understand the risks associated with toxic exposures, fire, and explosions, not only for the homeowners, right, but also for the installers and the maintenance staff. Even more when the HSC have identified in the past some common failures in understanding the ammonia refrigeration technology, mainly arose, and among others, the failures to potentially identify through assessments the likely sources of gas escape and how effective plant modifications could be implemented in order to control those sources of leakage. One of the things of trying, to control those leaks and the effects of dispersions is ventilation. And we do know basically from standards, like in this particular case, the BSCN 378 series, how important the mechanical ventilation is to be set in enclosed environments in order to try to mitigate the buildup of toxic concentrations of ammonia. But ventilation also plays a key and fundamental role in dispersions, right, of ammonia into the ambient, right? So how can advanced consequence modeling help in ammonia risk assessment? So, well, in this particular presentation, I'm going to talk about results that have been obtained by means of our more detailed type of consequence modeling tool called FLAX-CFD. CFD stands for Computational Fluid Dynamics. FLAX is a standard software for dispersion of hazardous materials, fire and explosion modeling in industry. It comprises different types of modules for different types of hazards that we tend to assess. In this particular case, I'm going to concentrate on the dispersion and explosion consequences. So talking about dispersion modeling, we do know that for toxic refrigerants such as ammonia, it is required to review the risks that are relating to an adverse release of refrigerant, that it could happen both inside a plant room, so an enclosed environment, or to the external environment itself, as for example, right, by cause of the activation of a pressure relief valve or extraction vents from energy centers. So careful design of heat pump systems, including this location and orientations of potential sources of release, is very important in order to reduce the risk overall, but also as well to provide evidence that practical steps in order to mitigate these risks have been adopted in order to prove these, not only to regulators, but also as well to planning authorities. But nothing comes without challenges. And the transport and dispersion, right, of these releases in urban environments is extremely complicated. Usually buildings or terrains cannot tell the flow fields, like causing updraft and downdraft, or channeling the flows in between different buildings, creating areas of calm winds, adjacent to maybe strong wind areas, and so on. So there is a very simple example, as possible to see on the pictures right on the right, called an obstructor, where basically you have like an oblique type of jet release that it's acting on a free field with no obstructions around it. So it's possible to see how the momentum-driven type of jet is been acting. While on the obstructed release, we have the same release conditions, but we do have on top of it an homogeneous, or let's say a uniform type of representation of obstructions, right, by means of blocks. And it's possible to see how the plume of the dispersion changes drastically by having simply, right, the add-on of obstructions. So this could affect them in the distances, right, over which releases that are harmful toxics, right, could vary. And ranging from tens of meters up to many kilometers. So terrain and obstacles should be modeled with high accuracy. I'll start with the outdoor release. Sorry if the last thing was not clear. Basically, I'm going to talk about 2 case studies, one outdoors and one indoors. One of the first case study is from the extraction bend release from an energy center towards the atmosphere. And what we would start usually with our CFD type of analysis is by developing very detailed representation of the surrounding and the buildings, right, that might be impacted by a release of toxic gas in this particular case. So we created a geometry based on the terrain importation taken from LiDAR data. LiDAR stands for light detection ranges. Basically, it's laser scanning type of information that we could import into our model, as it's possible to see on the orange colors right on the left picture. And on top of that, we create a manual representation of the buildings that are of concern. In this particular case, I mean the energy center, and some of the equipment that were going to be placed on the roof that are related to the ammonia refrigeration unit. So some of the results that we would obtain from dispersion modeling study, considering an original design of the bend stack release, as it's possible to see on the square box dash square box on the top left corner. That would lead to the release of ammonia, as possible to see on the right. We've used a color scheme based on the AGL or acute exposure guidelines for ammonia in order to represent what it would go from the light blue, the blue colors that would be representative of smell and or irritation contours up to more toxic concentrations. And on the square dashed box that is possible to see, it's basically the location, or that will represent the location of the air intakes, right, for the building, for the natural, for the ventilation, for the fresh air intakes of the building. So it's possible to see with the actual design of the vent stack for the most predominant wind conditions on the area. Upon a release of ammonia, there are high chances of ammonia getting into the building, right, by the fresh air intakes of the building. And with by conducting more detailed type of assessments and assessing different designs of the vent stack, as it's possible to see on the top left corner. Now we have included a 90-degree bend, 2 90-degree bends, in order to move forward or inwards, right, the vent stack in the building. We are observing that the concentrations of ammonia now wouldn't impact into the fresh intakes area, as it's possible to see on the white dash box again on the picture. So what we can basically conclude, right, from these case studies, that a redesign of the venting system was implemented in order to avoid high toxic concentrations of ammonia into the building's ventilation system. So using Flag CFD in this particular case, in conjunction with a representative 3D model of the topography and the buildings in the surrounding area, we could provide vital input to the design process. And the second case study, which I'm going to briefly talk about, is more of an overall type of consequence modeling study that would include not only just the release or dispersion modeling part of the consequence assessment, but also as well gas detection and or explosion modeling. So many heat pumps installation do include gas detection that is interlocked with isolation in order to mitigate, well, an ongoing release resulting in the accumulation of gas, which could be ignited by the flammable in a closed environment. So the idea with conducting, dispersion modeling in this particular case would be to assess different type of releases and test the proposed gas detector system in order to be suitable to reliably detect adverse releases of refrigerants into an enclosed environment. And if it's flammable, and it's for flammable gas, we could also conduct explosion simulations in order to assess the impact of those overpressures in the building, right, and potential damage that it could incur, right, into the installation or to the installation. So the idea with the explosion model would be to reduce, right, the likelihood and the severity of such releases and ignition scenarios. So for this particular type of case study, we are going to show the results obtained from an unmanned energy center, which is located in a basement location. It's a typical type of location that building companies try, to build or place the energy centers. And there are a few standards that could basically recommend against this type of locations, right, and basement areas. But with the right level of risk assessments conducted, it's possible to prove that the risks are allowed or as low as reasonable practical in order to prove that the design is safe to use. And this is what we tend to use for to basically work to tend to conduct for some of our clients. As we would start again with a very detailed representation of our geometry, in this particular case, a very congested area. And we would conduct ventilation studies. In this particular case, what it's possible to see are velocity contour maps on the left of the slide, and on the right, the velocity vectors. So with these, we can clearly see not only how the velocity or the ventilation works inside a building, but also have clear indications of areas of high ventilation, as it could be possible to be seen with or indicated by the red contours, or areas of reduced ventilations indicated by the red contours. So the next step is conducting a few dispersion modeling studies in where we would try to test, right, our detection system. And the idea is to try to challenge the system. And in this particular case would be about trying to set, based on the actual conditions, right, of the process, to set releases that would point towards areas of reduced ventilation, which basically will have an effect, right, of a less effective dilution onto the gas cloud. The leaks in this particular case, just for a clarification, are indicated with the blue arrows, right? So it's possible to see that the multiple type of directions have been considered, and we will conduct dispersions for different type of locations of leaks, but also as well different conditions. So it could be pressure, different release pressure, different hole sizes, and we would obtain results that's possible to see in this picture, where on the top left corner we start with basically the early stages of the release, and going towards the right lower corner, where basically the time starts advancing, right? So middle would be like middle stage of the release. It's possible to see that for this particular case, a full bore rupture. It's a very drastic type of release, but it's for indication purposes is quite clear to see how the gas would start advancing and filling the room until pretty much filling it, right? It's possible to see both top views and lateral views on the bottom of each corner. So what we would do, having the information from the ventilation and dispersion, well, we will conduct a gas detection evaluation, where we could test different type of detector layouts, as it's possible to see on the right picture. The red dots would indicate positions of gas detectors, of point detectors. So not only different numbers of detectors, as it's possible to see in the two top pictures, but also as well different locations of similar amount of detectors is possible to see in the bottom pictures. And we can test different detector set points, different voting criteria, different type of detectors itself. And with that, we would populate a performance table where we will have basically we will assess or check what are the detection times for the different layouts in corresponding to different dispersion scenarios, in order to have a sense feeling of which is the best performing type of detector layout. So the conclusions that we would have for this case study is that the ventilation system show poor performance in several areas of the energy center, resulting in the potential accumulation of gas in those areas. This would lead to the redesign of the ventilation system or alterations to the detection system in order to try to better perform upon a release of gas. So by using FlexCFD in this particular case, we can model more realistic releases of refrigerants into the plant rooms, assess where gas are likely to accumulate, and if the gas is flammable, what are the overpressures that would be generated upon ignition, right, of that gas cloud. So final conclusions in terms of what we've seen in this presentation is that small and large scale toxic or not flammable releases are credible scenarios with potential severe consequences. So predicting the dispersion of toxic and flammables in these complex environments is a difficult task due to the release characteristics, the ambient or internal ventilation conditions, and the topography, obstructions, even as well the process equipment, the congestion itself. So CFD can account for all this complexity and provide a more realistic prediction of the dispersion of toxic and flammable releases. The gas detection concept can be optimized to improve this, the detection is reliable, and also as well to improve detection times. And water pressures will be generated if such gas cloud is subsequently ignited. So all these will allow for a design optimization and ultimately results in reduced risk. So that's the end of the presentation. So if you have any questions, I'm happy to answer those later.
Brilliant. Thanks very much indeed, Pablo. That was a really interesting insight into this highly complex area of heat pump integration into energy centres. So thanks very much indeed. And yes, please do come back for the Q&A session at the end. Thank you very much indeed. Okay, so we invite Pablo to leave the stage and Matthew King. Excellent, Matthew. Thanks very much. So Pablo, super. And I'll hand you over to Matthew, who'll be talking about an interesting topic which picks up from one where Lyall's had lots of questions, Matthew. So interesting, which is practicalities of integrating heat pumps into distributed networks in place of gas-fired CHP solutions. So I think lots of people are quite intrigued as to what you have to say, Matthew. So I'll hand over to you.
Thank you, Simon, and thank you everybody for having the opportunity to present to you today. It is a big subject and a limited time, so I could talk about this much longer, but I'll hopefully condense this down into 15 minutes and touch on most areas that are key. So I'll start with Hilson Rand. So we're a multidiscipline consultancy with infrastructure design consultants, master planning and building design, MEP engineers, plus lots of different specialisms. We get involved quite early on and start looking at projects and larger projects where energy networks may be suitable. So it's quite important for us to assess the various different types of systems and the different permutations and optimize efficiency. So myself, I've been in the industry for over 13 years now, and since 2014 we've been looking at alternatives to CHP in early sort of design stages. So we've been looking at heat pumps and alternatives, and I'll talk through that. So I was going to cover system types and operating temperatures, but I don't think I'll do it justice as some of the other speakers, and opportunities really for reducing carbon emissions for the network and some considerations, and then going on to design sort of aspects and a bit of economics, looking at the practicalities of these things. So I'll just go on to the next one. So just starting off with context and key drivers. So implementing heat pumps within an energy network, the key thing is trying to keep the carbon emissions down, comparing it against a gas fired system, so CHP or maybe just standard gas boilers. Originally, back in the early days when we were looking at this in 2014, 2015, we were under massive penalties. So CHP was obviously far more carbon efficient because of the offsets reducing electricity. Now we're looking at far lower carbon emission factors, but I think the key consideration here as well in design stages is cost. Operating these systems and running them for residents and users is a key consideration. So trying to optimize efficiency, not only for carbon, but cost as well, is very important. So I was going to look at sort of the characteristics of heat pumps, and this is a vast subject in itself, but some of the key points. So looking at different heat pumps, you've got a performance envelope to be careful of, and whether that works with your network design temperatures. So be it an air source heat pump, you've got to worry about minimum operating temperatures and then upper temperatures, and also things like delta T's and things like that all go into impacting on the efficiency, and Ken's selection tools and so on, I imagine will be very useful, and it'll be good to get a copy myself of that. But some of the key things here is in terms of air source heat pumps, if you're adopting those, is the outside air temperature effects on COP, And if you're operating at higher temperatures, this further penalises you in terms of operating efficiency. So you can see in the bottom right diagram, it quickly drops the higher temperature. And this is a representative. It's obviously many different technologies, different refrigerant types that have different performances, but it's worth looking at these early enough, and because they do have different spatial requirements or different design requirements you need to consider, which some of these things will come on to. But the key thing about air source heat pumps or other heat pumps is the limited delta T. Unlike a gas system, they're fairly robust. Taking a very low return temperature across them can actually increase their efficiency. With heat pumps, you need to work within a limited window of operation, and you need to consider your size of units to avoid oversizing them, so you're shutting off frequently. So you want to avoid constantly turning off and on. They work a lot like a CHP system in operating at optimum efficiency if they work for longer periods at a consistent sort of condition. But there are different technologies in heat pumps that can overcome that, and it might be a case of different modules, different types of heat pump that will give you your true optimum configuration. And then just going on to modules, which a lot of that is to do with efficiency as well. So turn down part load efficiencies. You want to consider those at an early stage as well to impact on your plant areas requirements, especially for external air source heat pumps. You can quickly increase your requirements significantly when looking at different types and having modules, because they have to sit quite far apart based on the cold pluming and defrost issues. So going on to defrost, and Lyall did a great presentation on that, so I won't dwell on it too much, but it was more on the efficiency side and maybe the design implications. So I think a document to reference, which is very good and recently released, is the CIBSE AM16 document, and it came out frequently, and it does touch on some of these topics and gives a good all-round understanding to that. But just to give you some sort of indications or some rules of thumb, sort of when defrost will occur. I think it's very important when you're designing systems and monitoring carbon is the consideration of your weather data where you're designing. So we often design these systems in London, and I'm slightly London-centric in some of my pointers here, but I think this sort of methodology of looking at weather data and understanding how frequent the external conditions for air source heat pumps only, this doesn't occur for water-to-water connected to other devices, but air source heat pumps, you need to look at when the relative humidity is higher than 70%, when the temperature is below 5, and that will give you a sort of a time when you're going to have an energy penalty where the circuits go into a different mode, requiring to heat up the evaporator, which is the element that the air is basically an air heat exchanger, exchanging energy to the refrigerant circuit, and that will block up or be restricted in airflow, so reducing the output of your system. So it goes into a cycle of defrost that will heat up that heat exchanger and then rid your heat exchanger of frost. Those penalties, can be 4 to 10 minutes per cycle per refrigerant circuit, and that can happen 4 times an hour depending on the conditions. So when you're considering your COPs, it's always worth considering these penalties, and a few sort of selections or design considerations is looking at multiple circuit air source heat pumps. If you've got a single circuit, you'll have to find a reservoir of heat when you go into this defrost cycle, so that it will take energy from your network. Or if you go for a multi-circuit system, they can actually regenerate each other. So one circuit will go into a defrost cycle, the other one just purely provides energy at full operation to the defrosting circuit. That would obviously mean that you're not generating energy for the network, so you have to meet your demand by other means, and that's where you need to consider thermal storage or other supplementary systems or other modules of air source heat pump. So we would recommend thermal storage to improve your operation of the heat pumps. You don't have this constant turning off and on, but it also sized to benefit your defrost cycles and overcome issues with that, so that you can meet whatever demands, so peak demands on the network, whilst some of your units are in defrost operation for whatever period. And we sort of use a rule of thumb about 30 minutes peak load for thermal storage for your energy center. But we also, as a belt and braces at this stage, until we probably get more science to it, but the manufacturers are quite good now in giving advice, looking at an N+1 resilience, maybe for your early design stages, to account in your plant sizing and space take. The other key consideration here is when you're in defrost, you're obviously using up your energy reserve in the thermal storage. You need to then replenish that, and that may be during a peak scenario. So you need to allow for enough capacity in your air source heat pump to not only meet your peak, but to replenish your systems just in case you have a very flat peak. But that could all be analysed in details to overcome if you don't want to oversize your system as well, and then you have impact on your efficiency. So going on to system types, sticking to this sort of CIBSE CP1 definitions, the 4th generation systems, I like to call these high temperature instantaneous systems. So integrating heat pumps with this, you're having to operate at very high, relatively high, should I say, operating temperatures, so flows over 60 to 65 degrees, so that you can, your local HIU, your hydraulic interface or heat interface unit, is able to provide suitable domestic water temperatures to your terminals. The key thing with this 4th generation network is the ultra low heat losses. So over providing insulation and really minimizing your heat losses, because one of the key penalties in terms of carbon is the amount of heat that's just wasted from the system and isn't used. And that's a significant proportion. The air source heat pump side operating these high temperatures, obviously the COPs drop, and I'll go on to the sort of the limitation in sort of or the minimum operating temperatures is quite well constructed in a new CIBSE guide. I would also recommend looking at. It's been recently issued this year on putting sort of an industry point of view on domestic water temperatures, which previously there was a lot of sort of discussion on. So temperature modulating valves and so on, protecting your users from scalding temperatures, they require a minimum approach temperature to work safely. So often that's about 5 degrees, 10 degrees, temperature. I was thinking about HIU approach temperatures then, but that needs to be considered. So that's defining really your minimum network temperatures. And then the other consideration on your network is heat exchangers, which they can be a big penalty in terms of operating efficiently for your central plant. So it's worth considering those. Trying to change slide. And then, so when you're looking at these networks, some of the key considerations may be in operation and maximizing your efficiency is looking at additional supplementary heat sources. So waste heat opportunities are key ones. So maybe you can rely on water-to-water heat pumps connected to various methods, so surface, water, maybe it's an open loop or closed loop, groundwater. It's really site specific. So I would recommend at the earliest possible stages really looking into where are the opportunities, where can you find supplementary energy that will benefit your overall operating efficiency, but maybe also at these very low temperatures looking at a bivalent system design. So when your air source heat pumps, if you're using air source heat pumps in addition to these alternative heat sources, they operate very poorly and their capacity significantly reduces at these low temperatures. So backup by a water-to-water heat pump connected to a relatively consistent heat source would help you improve your efficiencies annually. And other things as well to consider is if you're looking at a 4th generation system and trying to minimize your additional sort of heat pump requirements, so having a water-to-water heat pump connected to a low grade or low temperature heat source into the system, you could also integrate only directly into higher temperature systems. So that might be industrial systems, industrial waste heat, be that incineration of rubbish and things. That there are a lot of schemes that we've worked on looking into those possibilities. But this is really trying to think outside the box and look at the opportunity, because this is where you can get some of the biggest carbon savings through your network design. And then the system that is emerging, and there's a lot of debate about this type of system and whether it is an energy network or not, but I'll discuss it anyway. This is the 5th generation system, and it may be somewhere in between. I think there was a question by Patrick earlier on some of the more distributed or local setups, and that's where you're in between here. So this system works quite well with heat pumps, because if you look, I didn't point out in the previous slides, but heat pumps, or certainly air source heat pumps, operate very efficiently around 30+ degrees, around that sort of envelope, and they don't have very good operation below that because of the step or lift temperature you have to consider. But they work very well with a ambient system, be it neutral temperature, or there's very many terms for this type of system, but they operate very efficiently, and the COP increases can be significant. So you could be looking at an air source heat pump operating at 60 degrees for a fourth generation system running at COPs of 2 to 3, but for an ambient system, you could be looking at maybe close to 4 or more central systems when considering the site-specific operation and external conditions. So these are very interesting. The other great thing, the other great benefit to these is that they run at neutral temperatures, so your waste heat losses are almost negligible, and you can then look at waste energy that's far lower in temperature. So that opens the window for many different types of heat recovery, and also recovering waste heat from the actual network itself. So having local heat pumps, and I didn't really go into, it's very similar to a conventional energy network, be it central air source heat pumps, or these could work with other heat sources, and then you have local heat pumps that step it up. So I'll go on to the next slide. It sort of tries to sum up that. So this is your central energy network in the bottom left corner, the central plant, so be this air source heat pumps, and then you have your distribution at its neutral ambient temperature, and then you have local heat pumps that step it up to a usable temperature for domestic water, so that could be 60 degrees, or it could be lower than that, so for space heating and so on. So that's compatible with radiators, underfloor heating, and other terminal devices. So these local heat pumps are within the residential units, and they typically within the service cupboard, and they have a space take of around sort of 1 extra square meter to the service cupboard. But that's sort of a worst case rule of thumb. Depending on your service cupboard requirements, you can reduce that, and I know they have got them down to 2.3, but the box size, these are of the size of 550 to 650 square in 650 millimeter square sort of footprint. Certain units you need to consider other ancillary plants. So I've shown on the screen here a local heat pump with a local buffer vessel. These local heat pumps, they operate in startup at full capacity. So you need to consider your system volume. And for a small residential unit, that system volume could be quite low. So you may need to supplement it with a buffer tank and then additional distribution pumps on the other side of that, because it almost acts like a low loss header. So you have a separate circuit for your local heat pump, and on other suppliers can overcome these issues, and it's all integral to the unit, but they're slightly larger at the 650 sort of notional, and you're getting capacities of operating peak capacities of between 4 to 10 kilowatts. There are larger ones on the system for maybe a high-end resi, but it's I'm just talking about your conventional high-density resi for the purpose of this presentation. So one of the key things here that they could be reversible, and that's benefits to the overall master plan. So if you're going into reverse and you're producing cooling to reduce heat in the resident units, that's future-proof in terms of climate change. So I feel that there could be issues in the future with climate change, with retrofitting air conditioning or DX systems that aren't potentially as carbon efficient as this system integral to a heat network, where your neighbour could use your waste heat to generate domestic hot water. So that's a great point. The other great consideration is often with resi, these high density resi schemes, you've got commercial to some degree, retail units on ground floor or amenity space that you can harvest some heat from. So whether that be a water or VRF system integrated into this system, it's a great story, because that will offset your central plant running and improve your overall efficiency, the carbon emissions. So that's a really interesting point. So I was going to go on to a case study of that. So on Manor Road in Canning Town, we're looking, and it's currently on site at the moment, and it's looking at this 5th generation network and some of the key benefits to this, and the reasons why we looked at the 5th generation. So the 4th generation, we didn't have enough plant space on the roofs for an instantaneous load, and I'll come on to diversity in a short while. So that was a key consideration. Also, incoming electrical supply, we estimate that we say potentially a six-figure sum in terms of incoming power looking at this system, because the operation is low in terms of instantaneous peak load on the central plant, and the saving was significant. We didn't have to have extra substations and so on in there. Also, for Manor Road, this gives you a position somewhere between a distributed energy strategy for residential energy network, where you'd have maybe the exhaust air heat pumps, and then you have the more central systems that need a central energy centre. And often the GLA in a London project would sort of demand that you consider a central energy centre in your first phase, which is a huge expense for developers and a massive space take, and where you would then develop on from there and add and supplement as you go through your master plan and add areas to that or buildings. You can then explore opportunities, because there are benefits to potentially breaking these new neutral or ambient temperature ambient systems down into block by blocks or building by buildings, because the delta T of the system in operation, your ambient system is a flow temperature typically around 25 degrees, but your delta T is only around 5 degrees, so your pump energy is significant. And I'll come on to breakdown of energy later on. But that also saved us around 500 square meters of plant space in the first phase alone, not having a massive central energy center and using roof space that would normally not be utilized, although it could be utilized for amenity space. But it was, in this project, it wasn't, but it was limited in footprint.
Matthew, can we try and wrap up in the next minute, please? I'm just
Sure.
We're overrunning.
Apologies. Okay, I'll do it really quickly, and it's a shame, but diversity factors for these systems compared to a fourth generation, we've got a consideration that your instantaneous load at the local units is far lower, so 4 to 10 kilowatts compared to an instantaneous based fourth generation network, but the diversity is far lower. And I'll rack on, because if you look at your domestic hot water profile, you've got a lag where you're reheating your local storage. So you have typically 180 litre domestic water storage tanks in there, and you need to reheat those, which takes time. So you've got a lag. So your diversity factors are normally higher. And we use the Hot Water Association, but you need to take into account this lag specific to your development, whether it be student housing or whether with certain peaks. So I'll try and wrap that up quicker. And then I was going to go on to, but maybe I could skip a lot of this, but the importance of exploring the energy story of these networks. So if you're looking at harnessing waste energy from whatever means, exploring what that means, and sizing your thermal storage so you can capture as much commercial waste heat as possible to then reuse to generate domestic water in summer. So that can be quite a significant amount of thermal storage to do that. And then how to get this through Part L and SAP calculations. At the moment, there isn't a solution in SAP to input local unit input energy. So you need to then use the workaround, which is a simplification. It may or sort of exaggerate the carbon emission saving at this point in time for these types of systems, but these systems are sort of equivalent to the CHP system before. So you can get with heating demand led fifth generation systems, you're sort of typically around 45 to up to 65% emission reductions. So you can get close to and above the CHP emission losses, but this is sort of a simplification. But when we looked in practice, I'll probably skip the metering sort of detail, but the energy difference between what's generated and input energy generated locally, or input energy used locally to the central systems, you've got approximately a 50 split. Then this doesn't account for waste energy. Then looking at these in comparison, and I'll probably skip the numbers and so on, the OPEX stuff in a moment, but the key consideration, or the key summary from this sort of slide here, is the amount of waste heat, because you've got local domestic water storage, is quite considerable. I think it's not included in the carbon emissions at the moment because it's metered and you're charging users, but it can be a significant proportion there. And then there's different OPEX, but I think the key consideration here is when you're reducing your central plant annual energy demand, so the commercial opportunity for ESCOs and so on is reduced on the resi side, but then you're opening your system up to new users, so commercial units, resi units, which have a significant energy demand in winter, but also this opportunity for reducing your central plant operation can present profitability and economics there, but you need to consider that on a scale.
Thanks very much, Matthew. Sorry to call you to a halt, but we are running well over time now, I'm afraid. So we'll have to leave it there. There are questions in the chat, and I think the important point for people attending today is the focus on district heating network. So the whole question of fourth versus ambient loop is something we'll be dealing with another day. But there's an interesting question from Daniel Cookton about the total COP in the chat there, Matthew, which I think was what merits having a look at. So thanks very much indeed, Matthew. It's really appreciated you speaking today. Please stay around for the Q&A session. I've got to try and keep things to time, otherwise we find people drift away if they don't come online and expect the presentation they're expecting to see. So we'll now move on to David Birks. So David, if you don't mind coming online, thanks very much indeed. So David, your presentation is about open loop ground source heat pump systems, and without further ado, I'll leave you to it. Thanks very much indeed, David.
Thanks, Simon, and thanks everyone for joining. I promise I'll keep my talk to less than 10 minutes because we are running a bit over. My talk is entitled Groundwater Fed Water Source Heat Pump Systems Coupled to Heat Networks, and I'm going to talk about where I think that these systems may perform well compared to other low carbon technologies. Simon, okay, got it. So sorry, the first two slides are just for general context. We've had 270 years plus of burning coal, which obviously sparked the global industrialization and huge societal change. The use of coal in Europe and the UK started diminishing in the latter part of the 20th century and has now all but stopped. But the use of coal elsewhere is still very high, and our burning of coal still, globally, is at levels is still at the highest levels ever. In the latter part of the 19th century, hydrocarbons, that's oil and gas, came to the fore in terms of our sort of combustion energy sources. I actually began my career as a geologist mudlogging in the southern North Sea, drilling for gas in the early 1990s. So we've had 2.5 centuries of fossil fuel burning, and we believe that really all of this is about to change, and about to change because of global warming and climate change. So what does the sort of new low carbon future look like? Well, this is a table that I lifted from Bay's Green Heat Network Fund 2020, Call for Evidence. And you can see that heat pumps are a very dominant technology and likely to remain so, I think, for the next 10 or 20 years at least. There are really two main types of heat pump. There's an air source heat pump, and then everything else, whether it's water source, it's open ground source, mine water, or sewer, it's liquid source. So we've got air source and water source heat pumps are our key heat pump technologies, and I believe that it's going to be economics that will determine sort of selection of one type over another. Yeah, so moving on to the next slide. This is what a large air source heat pump looks like. I think it was until recently the largest air source heat pump in the UK, 700 kilowatts. And linking back to Lyall's first talk, obviously with an air source heat pump, there are issues with cold nuisance and noise. So whilst the size of the unit itself is very similar to a similarly sized water source heat pump, the area or the space around an air source heat pump, which effectively could become sterilized, is actually quite a lot larger than the unit itself, and I think is something that should feature into the capex evaluation of this and other technologies. I think there's a general presumption that an air source heat pump system is a lower capex option than a water source, because you're simply sucking in the air which is ever present, rather than having to couple to an external water harvesting network. This is the heat pump that I believe is earmarked for the Colchester Northern Gateway. As I said, it's actually of a very similar dimension to the air source heat pump that I showed you earlier. But the main difference is this doesn't require an airflow from and to it. And so these systems can be hidden in a basement. In a basement area, as opposed to being external to the building on a roof space or in the periphery of a building, and requiring measures to hide the visual and the air nuisance and the noise impacts. So these are sort of, I think important elements of the CapEx evaluation between water source and air source heat pumps. And of course, we believe that water source heat pumps generally do have a higher coefficient of performance than air source heat pumps. And so over a longer time frame, the economics can start to favour water source over air source. But a water source, or in the case of groundwater fed heat networks, the water source heat pump has to be connected to a well field where the groundwater is harvested. And that well field is a considerable CapEx consideration. And here is the borehole configuration at the Colchester Northern Gateway, where we had 2 abstraction boreholes drilled to depths of 130 to 200 meters and drawing water from the chalk aquifer, pumping that water over a distance of over ½ kilometre to re-injection boreholes where the water is put back into the ground. And generally, that's a licensing requirement in the UK to preserve groundwater for other uses than just heating and cooling. These wells have to function to a very high level of performance and have to be very durable. So for the next 25 to 50 years, we're going to be pumping 50 to 60 tons an hour, 7,000 to 8,000 hours a year from these abstraction wells to these re-injection wells. So it's not just a matter of constructing a high quality installation, it's also a matter of maintaining it and looking after it during its working life. And that, in my opinion, has a cost. Well, it does have a cost, and in my opinion, that cost is probably 3 to 4% of the wellfield CapEx. This is showing the typical arrangement for drilling a chalk water well. It shows a 35-ton rotary rig, a recirculation pump where the drilling fluid is pumped to and from the borehole, recirculation tanks where the drilling slurry is filtered, and this is all typically sort of enclosed within a fenced compound. And this is the sort of typical dimension required for drilling a chalk water well, such as that drilled at the Colchester Gateway. And this setup would be required typically for around about 6 weeks per borehole. But when the drilling is finished and the borehole is sort of capped off and complete, the actual surface expression of a water well is very, very small indeed. Here we have an abstraction well at the Royal Festival Hall, which just pops up into the basement area and then links to the plant room. And here also at the Royal Festival Hall, we have a borehole external to the building, installed in a street and enclosed in a manhole chamber. So very low surface expression. Okay, moving to the crux then, which is, okay, the economics behind choosing water source over an air source. And I'm going to start with the extra over CapEx. So for the water source heat pump system, the borehole infrastructure at Colchester Gateway costs around about £700,000. So per megawatt, I'd say a typical extra over capital cost for a well field is of the order of £500,000 to £1 million. I put a question mark next to air source heat pump because I don't know how you monetize the sterilization of space and noise and actually putting a value on the space occupied by an air source heat pump that could be used for other purposes. But I'm sure it does have a CapEx value. And in some instances, that CapEx value may be approaching or even more than that of a water source. We know that coefficient of performance of an air source heat pump is lower than water source heat pump, 2.5, 3.5 to 4 for a water source heat pump. So what does that actually mean then in terms of the Colchester gateway? Well, if assuming an electricity cost of 15 pence a kilowatt hour, and assuming we're producing 8 gigawatt hours per annum of heat, so it's a sort of a modest size heat network, the electricity cost utilizing air source heat pump technology to provide that heat is just under £500,000. Whereas the same with the water source heat pump would be £250,000, so substantially lower within the first year. And looking at this here, within 5 years, one would expect the extra over capital cost of the well field to sort of be compensated within about 5 years, and thereafter the cost savings are become fairly considerable. And looking at organisations such as PFIs and local authorities who are looking at whole life periods, who are looking beyond the 5-year payback period, then you start to see that water source heat pump technology starts to come into its own. But, and it's a big but, water source heat pump technologies, the business case to work, these higher coefficients of performance have to be sustained. And attaining and maintaining a high COP in a water source heat pump system, there are 2 things you've got to meet. One is a stable temperature, and that links back to, I think, Ken's presentation earlier. And the other is a stable pumping regime from the abstraction boreholes to the reinjection boreholes. Okay. This is actually from my PhD thesis, and it shows 6 years of monitoring of abstracted groundwater temperature at Green Park Underground Station, and it shows that the temperature of groundwater was, despite these small, probably mini breakthroughs, the temperature is stable throughout the year between sort of 13 and 13.3 degrees. There's no rising or falling trend in the groundwater, and that's the kind of trend that for a district heat network we have to aspire to. So that's the temperature issue. Also from Green Park Underground Station is we need a stable pumping regime, and at Green Park it wasn't stable. It wasn't disastrously unstable, but there was, and it's depicted here by the green trend line, which is flow rate into the reinjection well, by the green, and by the blue, by a rising level in the reinjection well. And after 6 years of operation at Green Park, we had to reduce the flow rate, and therefore the system performance reduced at that point to keep the reinjection water level at an acceptable level. So at Colchester Gateway, and this is what the configuration looks like in plan. So there's 2 abstraction wells, 3 reinjection wells, and there's about 600 to 700 meters between abstraction and reinjection. That distance is what I believe is needed is to maintain that stable water temperature for at least a period of 5 to 10 years before we can start to balance heating and cooling, and that's important. And then also Colchester Gateway, this is looking at the hydraulic parameters. And what we're looking at here is a period of 1 week where we were abstracting from 2 abstraction wells, each at 9 litres a second, so about 35 tonnes an hour from each. And this resulted in the abstraction wells in a drop in water levels of around about 40 meters, and a rise then in the reinjection boreholes of about 60 meters, and then starting to stabilize towards the end of the interval. And it is, but bear in mind this here is just a week, and we've got to be maintaining this hydraulic stability for 1 year, 5 years, 25 years, 50 years, and that requires good wells, and it requires a degree of investment into looking after the system through its full working life. So I've finished my presentation here. There are 2 key parameters: stable water temperature, stable pumping regime. With those 2 things, we will get the highest COP from a groundwater fed heat network. And I will finish, or rather my penultimate slide is just lists my research in this area from the mid-2000s to today, looking at the risk profile, and some of these may be of use to anyone interested in groundwater coupled heat pump systems. And that's the end of my presentation. Thank you all for listening.
Brilliant. Thanks very much indeed, David. That was really appreciated. And thanks to all speakers. If Tom, if you don't mind taking David's presentation down, and if I could invite speakers to come back onto the stage, please. There's been an awful lot of questions during the time we've been speaking, so it'd be great. Matthew, thanks. Lyall, well, I hope you're still there, Lyall, because I've got questions for yourself as well, although I appreciate you've answered a few in the chat. We'll give Lyall a second to see whether we can join, otherwise we'll have to run with what we've got in terms of the chat from Lyall. So as well, without Lyall joining us, we'll move on to the first question, which I've scrolled to, which Lyall hasn't responded to, which is from Jared. So Jared's asked a question. I don't know whether either Ken and or Matthew would like to respond. What seasonal coefficient of performance do you typically aim for when planning an air source heat pump design to make it viable? Would either of you be able to jump in on that one at all? Oh, Lyall, you've joined us. Excellent stuff. Thanks very much indeed.
Apologies.
We'll back up the bus and we'll try to do this in order then, please. So Lyall, there was quite a lot of questions. A lot of them focused on the temperature. Oh, you've gone again. The temperatures of your system. I suggest you stop touching things, Lyall. The temperatures of your system, particularly, and then the interaction of the emissions, etc., the airflows. Could you just sort of summarise some of the responses you provided to the questions that have been asked? Because I'm not sure many of the delegates will have been reading the chat as it's been going on, so that'd be really helpful, Lyall, if you can particularly.
Oh, I'm just going to try and get this. Sorry, I'm working on my phone here.
That's okay. So can we just quickly cover temperatures, please, Lyall? A lot of questions asked, which you've responded to, about the fact it was an older, higher temperature network and how you approach that, and what you've been doing.
Yeah, so it is an existing system that's that will be fed by the CHP, and the intention is that we'll retain the existing CHP and essentially put the new air source heat pumps in, and they will work kind of in tandem, and over time will soak up the contribution that CHP would have otherwise been contributing to the overall heat demand. Obviously there's going to have to be matching of the temperatures there. Unfortunately, with the scheme that we're looking at in particular, it was operating on an 80-60 flow and return temperature regime, which means that integration of heat pumps within that is a lot simpler than we're seeing in other networks. Certainly where you do have CHPs operating at 90 degrees, that's going to be a real issue for integration of heat pumps, because as Ken will be able to tell you, we can typically even the high temp heat pumps, we can get them up to 80, but getting them higher than that is a real issue. And it's the same thing on the return temperature side as well. There are limits to the return temperatures that these heat pumps can operate with. So it's the same message with regards to operational efficiency of the networks. Whatever we can do to reduce temperatures will benefit the ongoing operation, but it'll also mean that integration of the low carbon technologies will be a lot simpler. But certainly where we are starting to introduce heat pumps in tandem with CHP, that's going to have to have we're going to have to have a lot of thought about how that's practically achieved with regards to the temperatures.
Okay, and sort of a question that's popped up in the chat, and I suppose sort of is similar to a lot of us. How are you thinking about configuring the CHPs with the heat pumps? Are they running collectively at the same temperature? Are the heat pumps in some way preheating the CHP? How's that worked? Have you thought through that hydraulic modelling yet, or is that still too early?
Yeah, typically we'd look to run them in parallel. We have tested and investigated kind of heat pumps in series preheating feeds to the CHP, but for a number of reasons it's not always viable. It essentially means that you would have to always operate your CHP in parallel with the heat pumps, which then then begs the question, why are you putting heat pumps in the first place? Why wouldn't you just run the CHP? So I think what we are investigating is obviously run them in parallel, and there's another piece of work that we're doing in investigating marginal emissions. and the effects of marginal grid emissions with respect to operating heat pumps, because obviously on an average basis, running heat pumps or running an electrified heating source is going to be better carbon wise than running a CHP, but that's not true all the time. Sometimes, when if it's not windy, or if there's a large proportion of gas or even coal on the electricity grid, running a heat pump is not necessarily the best thing to do from an efficiency and or environmental standpoint. So that's something that we're looking to investigate, and how we marry up operation of the CHP and the heat pumps together, looking into a kind of smart dispatch idea where we can operate or sequence the heat pumps with the CHP based on what's best at that time environmentally. And then similarly, there's also the economics that play into that. So the variances in electricity tariffs over day and night will also obviously impact the economics of running each of them independently or in parallel.
Okay, and just before we get on to one of the other speakers, just a very quick question. Can you just sort of confirm where you are in the actual development process? Because you responded to Michael Halcrow about integral to the REBA concept design. Is this now progressed to something you're constructing, or is it still in development stage, Lyall?
So it's in development stage, awaiting a few things. So it's basically just confirmation that the new phases are actually going to get built, and then there'll be a period of kind of commercial negotiations and tariff renegotiation to then give us the green light to go ahead. But we've developed it to the point that the solution is basically ready to take to planning. So as soon as we get that consent, we'll look to take it to planning, get planning permission, and then develop it to REBA 4 stage.
Okay. So moving back up the questions, and I'm not sure who this was aimed at, but the one from Jared, I don't know whether anybody on the on the call wants to take this one. This is about seasonal coefficient of performance in terms of air source heat pump design to make it viable. I could move on unless anybody feels that they're happy to sort of respond on that. Okay. Ken, jump in, please.
Yeah, I can take that. The calculator, the SCOP is actually a list of compromises in many ways. The target, of course, is to maximise the SCOP, but we have to take in a number of considerations: the refrigerants, the number of compressors, the capital cost of the equipment, has used influences, even down to the speed of the fans and the evaporators, and the impact on noise. To take Lyall's point, the impact of cold air. And all this goes into the mix, and the SCOP inevitably is a compromise. So it's a much more complex design process than you might imagine. It is not just a 1 megawatt heat pump. There is so many considerations to be brought in to the debate. One of those, of course, is what SCOP do we want? Clearly, we're always aiming for 3. On air source, do we always achieve it? No, we don't, because we have to compromise in some direction or another. Water source, I would suggest we're aiming for 3.5 towards 4. But there's, we're not living in a perfect heat pump world, unfortunately, especially on retrofit. New build, we've got a better chance. But retrofit, we do struggle, especially when we're dealing with older buildings.
Okay. No, thanks very much indeed. There's an interesting question from Andy. I'm not sure that any of the speakers can answer it, but I'm intrigued whether any have done any analysis looking at the cost effectiveness of reducing the flow temperatures in existing networks, by modifying user systems to improve the overall viability, and the trade-off between improved central plant efficiency versus the actual cost of undertaking works potentially in each building or retrofitting dwellings to lower flow temperatures might be something a little bit early. People are still thinking about that. I don't know whether any speakers got any thoughts on that particular subject.
Well, again, the work I've done over the last 3 years is very often on a retrofit. I'm afraid that the conclusion does very often come down to bivalent system. Rather than rip out the gas boilers on many systems, it's better to actually let the heat pumps do the base load, let the boilers top up the system, and then leave the radiators and the existing pipework in place, because it's not just a replacement of the heating system; it's all the redecoration work with the disruption that has to be thrown into the mix. So on retrofit, I think it's not difficult to actually say that bivalent it probably is the best way.
Okay.
Just to add to that, Simon and Ken, there's lots of design issues when you're looking at trying to reduce the temperature. So delta T's is one of the most one of the biggest issue with what you can get in terms of flow and meeting peaks still with the previously sized or the historically sized infrastructure, and then there's a significant cost in changing local infrastructure. So you have to look at those design implications, but that's why maybe future-proofing energy networks for extension and things like that has a penalty initially, and that's often why they weren't done. But you can look at maybe the fifth gen design if you're going down that in terms of future-proofing it later on, so you can enhance it. And it's not, there's a lot of talk about that being future-proof in itself, but you have to consider it in the design early on. But yeah.
Okay, no, thanks very much indeed. The one from Michael's interesting. So Michael Checkley, so his question is, we've seen examples of air source heat pumps not delivering what's expected in some social housing, leading to high electricity costs for residents. What are the most common reasons for those air source heat pumps not delivering the expected benefits? So I suppose picking up on some of the points that Ken's made, but maybe Lyall or Matthew, some sort of really obvious mistakes that people are making when incorporating air source heat pumps into new build developments. Would anybody like to pick up that question as sort of the sort of thing where you rock up at a site and go, oh no, they've done this, or it's not working properly, or etc., etc. Would anybody else like to jump in and pick up any points? I'm thinking of particularly possibly location of the air source heat pump, integration, possibly the temperatures that were expected to be operated at versus the actual reality. I expect most probably the response would fit into one of those categories.
I think, unfortunately, most of the poor installations I've seen have nothing to do with the heat pump. It's been sort of poorly specified, and I can only conclude that they've been poorly designed. The Danish, of course, expertise is there. And I don't think there's been that expertise until recently in the UK. I think it sounds a bit of a blunt statement, but I'm afraid that's the only conclusion I can draw.
Okay.
Yeah, I would add to Ken's point that I think the design is probably not maybe being compatible with the heat pump technology that may be being installed. So adding in hydraulic brakes and things like that increase temperatures and require the heat pumps to operate at higher temperatures is a penalty to the efficiency. And then also thermal storage, not considering the operation, so constantly starting the heat pump because it's intermittent operation has a penalty in terms of energy as well.
Okay, no, right. Thanks, Matthew. Yeah, really, really good and important points for people to take into account on the at the event. Pablo, I'm conscious there was a question for yourself, just a very quick one for Karina, which you've responded to. The sort of the time when do you usually get involved in a project, and when do you think it makes more sense for you to kind of get involved? Because I'm conscious that modifying it rather than relying on detection is a different way. Any thoughts on you'd like to add to your response to Karina at all, Pablo?
Yeah, it's certainly, I mean, a good question. I mean, some of the problems that we tend to encounter, right, when designing, I mean, this kind of installations is that, well, the risk aspect, right, of risk and safety is taken right at the side, and then it comes into when commissioning, right, or even as well, not commission, but when the approval, right, from operations is down the line, then people start thinking about, well, we should need or get approval from regulators or as well from councils in order, I mean, to run them in this particular scheme. So early phases, right, of the design would be the ideal point where we can start having a look at, well, particularly through hazards or hazards, right, to identify early stages, right, of hazards or potential hazards on the line that could be quickly solved by performing different type of consequence modeling studies.
Okay, lovely. Thanks very much. Matthew, Connor's question about, because the focus of your first part of the presentation was obviously about reducing losses from those higher temperature networks. I'm not sure whether you would have one, but an interesting question about the rule of thumb for heat network insulation thicknesses and conductivities, or possibly even the percentage of heat loss you'd expect. Any thought on that one, Matthew?
It's very much on the pipework system design. And I didn't want to dodge giving a rule of thumb because it's like dangerous, but there are some sort of there's some good advice, I think, in the CIBSE guidance on what you should, on CP1, what you should be looking at and how to calculate it. But it's an early consideration because there's different configurations of pipework risers and so on that can have a huge impact in thermal losses, and you want to avoid your system pipework length and so on to avoid having to insulate it all. But I think also that there's a key consideration as well is how the user impacts the return temperatures and losses as well. So you need to consider all those things. But there are some rules of thumb. Probably not the place to put it out here. We have internally, but you need to be mindful that it's more than you would imagine for a fourth generation system now to get it as efficient as possible.
Yep, no, completely agree with you there, Matthew. Thanks very much indeed for that response. I'm not sure that you could answer it on this course. It might take a lot more, but the one from Ben about the waste heat from a network substation, rough guide to the size of a substation. I'm not sure that's something you could easily answer, but I flagged the question up. Matt, has it been answered?
I can answer that. So there's some interesting sort of case studies done by, I think, SSE in the past. I think they've mainly been based on using the waste heat with a higher temperature energy network. So it might be good to look at that again and look at the viability now. The cost of electricity may go down in the future, but also the COPs and so on for a low grade system if you were going to utilize that. I'm not advocating either one, but there is a lot of advice out there. But at the moment, when we've looked at it in early stages for projects, you're looking at network size substations to make it viable. There's huge challenges in getting the energy networks to agree to doing anything from their usual standards. So quite often we just have air-cooled transformers and so on in this country, going to a water-cooled transformer and then having to overcome issues with resilience when you've got a water circuit coming from their transformer, which is tried and tested technology, but it's if your system doesn't take enough energy, how there's enough space for dry air coolers and that critical resilience. And it's quite a painful process. So I wouldn't really go down that route unless maybe down the road we're trying to find those little smaller improvements to hit net zero, and these suddenly become cost viable. And these energy the DNOs are willing to consider it more, and hopefully they will. But network size substations is really when you get into the opportunity of recovering heat.
Okay, Lyall, I'm conscious you responded to that with your link, so thanks very much. Anything you wanted to add to what Matt was saying?
Yeah, I don't think the importance of transformers as a source of waste heat can be overstated. The temperatures that we'd see from the oil coming out of these things are in the kind of anywhere between 30 and 60 degrees. Now, and that's continuous 24/7, 365. These network size substations are operating all the time. And if you think about, when people will demand the most heat, is typically when people also demand the most electricity. So the load profiles for transformers and heat networks match up quite well. And obviously with those high recovery temperatures, comparing, 50-degree water on a continuous all year round basis is, the impact that would have on COP is quite substantial, to the point that in some cases you might not even need a heat pump. If you get a low enough temperature network, you could just have direct heating from the transformer. So we're huge advocates of the potential for this technology, and are obviously trying to drive it as hard as we can. But as Matthew said, the engagement with the DNOs is the hardest bit. It's out with their business as usual, and their job is to keep the lights on. So whenever you have to do something other than that, it can be quite difficult. But we are making progress, albeit slowly. But we're getting there, and we're at the opportunity where we're looking to do a live trial of this heat recovery system in the new year.
Okay, cool. Oh, that's good news. I'm conscious we haven't brought David into the chat yet. So David, there's a couple of questions for yourself there. One is from Andrew Hart about minimum distance between extraction and rejection wells. Any thoughts on that one, David? What's the minimum you think is acceptable to go for?
Yeah, I do. Very strong opinions, actually. I think for a district heat network or cooling network where you're harvesting or extracting gigawatt hours per annum of heat, then it is several hundred meters separation between abstraction and recharge, definitely, particularly in chalk, but I'd say in most other aquifers. And even at Colchester, where you've got 600 to 700 meters separation and sort of 5.5 gigawatt hours per annum of heat extraction, that thermal mass or thermal volume, it is finite. So if you keep taking the heat out of it, in 10, 15 years' time, the temperature of the abstracted water will start to change. So I think it's true for any ground source system is that there has to be an aspiration to balance heat inputs and heat outputs, and that goes for heat networks and it goes for large buildings. So yeah, that's my point on separation.
Okay, and while we've got you on the stage speaking, David, there's a question at the top from Michael Taylor that's come in. So hi, David. Thinking about the regeneration of boreholes to maintain source temperatures, better to provide more boreholes or regenerate. So really, I suppose the general question is, how do you maintain that source temperature? I mean, you've got the distance factor as well, which we've just spoken about. Are there any other thoughts on this in terms of maintaining that source temperature over the life of the project?
Yeah, the only other control you have other than distance between abstraction and reinjection is managing your heat inputs and your heat outputs. That is the only other measure you have. That's something that the ground source community, in my opinion, has not really understood particularly well in the last 10 or 20 years.
Okay, thanks very much. And I'm conscious we've still got quite a lot of people on the event, although we've run well over time, so that's really good news. Lots of interesting things. So this event was about the practical application of heat pumps to district heating networks, but I'm conscious that Matthew opened up the window to the very contentious world of fifth generation, or what I would call ambient loop networks, because I'm sorry, I'll just be blunt, I don't think there's such a thing as fifth generation networks. I think they're ambient loops. They're a very different kind of technology, and I think it helps for people outside the sector to differentiate between those two, but that's just my personal view. Matthew, to sort of close, quite a lot of questions, and I suppose lots of questions in my mind about that whole life cycle cost for the customer. And I'm conscious maybe Lyall might have some thoughts on this possibly as well. What you're thinking, because there seems to be a lot of questions unresolved in my mind in the sector about what the end cost to the customer is. I appreciate that it might be capitally less expensive potentially than a heat network, but what's your thoughts on this one, Matthew?
So this is something that we've looked into, but now we're starting to engage and constructing and starting to get to that point of handing over to Building Co and ESCO people, and it's very interesting from what we originally thought. So the maintenance costs of central air source heat pumps are less than a sort of a gas network, from my understanding, and when we worked through with experts. But the issue is the local heat pumps, when you're looking at fifth generation, is the life expectancy of the units is only 15 years, and they're more expensive than a HRU. So there's an escalation in costs in terms of basically replacement costs in the lifetime of the system. So typically ESCO would maybe be 30-40 years maybe. So there's a few different replacements. So this gets down to then discussing the ownership line potentially, and then putting the onus maybe on the residents if they're private residents, or the operators if it's affordable housing, which may not be acceptable. But we've been through those discussions, and often they can take ownership of them, but there's also service charge requirements, and there's benefits if the ESCO owns the local heat pump as well. It's very much like a HRU model, but the issue we find is the replacement costs being higher. But I mentioned it earlier, the future-proofing these systems so that you can allow cooling is often something that maybe in 15 years' time we're going to find that these units would be replaced anyway to provide cooling in these residential units because of overheating reasons. So although that doesn't answer the question, but they are comparable when you look at it, the round, but you do need to be careful.
Okay, no, that's helpful. Lyall, you don't have to, but I wonder whether you've got any thoughts on ambient versus district heating network and where SSE is sitting on this at the moment.
Yeah, again, it's something we've looked into quite extensively. Certainly, we've still got questions around the capex comparison. The OPEX is a separate issue, but the OPEX on the billing and metering strategy is another whole issue. But certainly on the CapEx side, where we've done comparisons, we've costed up ambient loop versus traditional or conventional DH network systems, and it's in the orders of multitudes higher for some ambient loop systems that we've looked at. So that's obviously an issue that we need to look into and discuss further. One thing I would add on the future proofing aspect though is, we know that technology is going to adapt and evolve and develop, and looking at a kind of 30-40 year ESCO period, that's a long time, and that you're going to get huge technological advancements within that period. And if we start thinking about decarbonisation, it's a lot easier to decarbonise a heat supply at a centralised energy centre and swap out technologies and install higher efficiency heat pumps or whatever. It's a lot easier to do that on a centralised case than having to then go in every 10 years and swap out everyone's technology on an in-building level. I think the consideration of the potential that you might have to do that, and in 10 years you're gonna have to go and swap out these heat pumps on an individual basis with newer, better alternatives. It's just the cost associated with that and the impact to the customer is pretty substantial. So our opinion is very much still that the centralized DH network is the best thing in terms of future proofing a low carbon heat supply.
Okay. No. It's best for me not to express an opinion because that would be inappropriate, because there's lots of different solutions out there. But what you say makes a lot of sense. I'm conscious we are really running up against time now. So just David, one final one, and I thought it was quite contentious at the top. So clearly CIBSE has published a document, which I believe is the CIBSE one, CP3, which is about the distance between abstraction and reinjection. So they're suggesting 100 meters is sufficiently good for a district heating network. I don't know the specific reference. Maybe that's a much smaller system. What's your thoughts on that one, David?
I think CIBSE are wrong.
Right. Okay. Well, there's a very clear response from the expert on the call. So it's it's not for me to say right or wrong, but I think that's a very helpful response, helpful and clear response. So I think we best wrap up. We've got people dropping off the call now. But thank you so much to all the speakers. Thank you for your presentations. Thank you for being involved this morning. Thank you to all the delegates who stayed on the call. And just big thanks to everybody who's attended. So thank you again. And Tom, if you'd like to wrap it up, I think we'll call that a day. Thank you very much indeed.